Let's start. I will be handing over the stage to you. Hello everyone. Welcome back to another session on Sunday Citadel. And we are here we have with us Mr. Sanjiv Wazir, who is marine lubrication expert, one of the best people to learn marine lubrication and tribology from. And we are very, very thankful that he is conducting today's session. And we are very honored to have him. So as more people join in, I won't take any time further and hand over the stage to uh, Sanjiv Wazir sir. So before starting the session, if he can share his interesting journey, how he got into tribology and marine lubrication, and some of like his educational background from IIT Bombay and much more, so that we would be happy to hear his own journey before we start the topic. So please share, Sanjiv sir, your journey into marine lubrication. Before starting the session. Yeah.
Okay. As you mentioned, I did mechanical engineering from IIT Bombay, and my whole family actually was in the marine industry. My dad, we are actually Kashmiri Pandits, and he moved to Bombay in 1950, and somehow ended up joining. I mean, there were people known to him who persuaded him to join Malabar Steamship Company, which was around like a contemporary of Scindia's, I think. So they were having some ships, and the owner of Malabar Steamship Company felt that he had some potential to become an engineer, and sent him for training to workshop in Bombay, marine workshop in Bombay. The name I forget, it was later on taken over by Masgondam. Anyway, so he became a marine engineer and started sailing. And then actually my uncle, his younger brother, also joined, and another uncle also later on, I mean, over a period of time joined. So it became a more of a marine sort of oriented family. And I did my engineering, and of course, as you like half my batch, for example, went over to the US and things like that. But I wasn't so keen on that. And so I mean, I'd sailed with him as a kid. I had sailed with him, and I liked that sailing experience. So I went into marine engineering and did a year in Scindia workshop actually, and then joined SCI. For about 7-8 years, I was sailing with SCI, and then joined some foreign companies. In the meantime, I'd of course cleared my second class, first class, etc. Joined some foreign companies a couple of years back. And then in the meantime, my dad had started a marine ship repair workshop in Bombay. And so I joined him. No, sorry. Instead, I came ashore by the time I'd got married and had a child also. So gave up sailing, joined Garware Shipping as a superintendent. And then actually joined the workshop which my father had started. And then in the meantime, actually Chevron Marine Lubes was looking for somebody to represent them here. And I put up my hand, and they somehow picked me up. And then, so for 4 years, I was managing Chevron Marine Lubricants in India, and we grew the team quite a bit. They didn't have anything when I joined, and like at the end of 4 years, we had about 40 vessels or something like that. Then Chevron and Texaco got, I don't know if you're aware, Chevron and Texaco merged. Chevron actually took over Texaco, but the marine lubrication part of Texaco was a bigger entity. So my business actually went to the Texaco part of it. So I then went back to my workshop business, but in the meantime, BP, Mobil, and Castrol actually, maybe they had kept tabs on the market. So they approached me to, can you work for us? Like, and so eventually I started working with BP. And in the meantime, actually, I'd become quite interested in lubrication from a technical point of view because I'd sailed and also had a engineering background. So I started doing some courses, and I had in the meantime got something called a certified lubrication specialist kind of a certification from STLE. STLE is a worldwide Chicago-based organization, but it's all over the world. Society for Tribologists and Lubrication Engineers. So they had these courses, and so I've done that also. And some of my, like Varun Shipping was one of my customers then, and they had started a training workshop, training center, and they asked me to start giving lectures over there. Started doing that, and then this started this revalidation course started. So many of the institutes around Bombay, they asked me to give lectures on marine lubrication in those lectures. So that started off my lecturing or teaching kind of this thing. So since then I have been giving lectures in many places. Lately, in the last 4 5 years, I think mainly at the Institute of Marine Engineers workshop, training center in Nerul. But also elsewhere, like I've given lectures at Torani Maritime Institute and so many like MIT in Pune, etc. And also the Institute of Marine Engineers branches in Calcutta, in Chennai, etc. Those places also have given lectures. So anyway, I got interested in the back end of instead of the selling of marine lubricants, I started getting more and more interested in the technical part of it. So I've been doing that. And then with BP and later on with Lukoil, got involved in the technology part of it in a major way, starting of course with lube charts and vessel visits and so on. And then trying to contribute also in the formulation, etc. So we have, especially with the Lukoil team, Lukoil technical team was Germany based. So had a lot of interactions with them and some suggestions of mine also got, got sort of used in the process of developing lubricants and etc. And also in usual analysis, things which I would have liked to see, but was not seeing in the analysis reports earlier in Chevron or BP. In the meantime, had developed some ideas about what we should be testing and so on and so on, especially with hydraulic oils, etc. So that got implemented. So it was good experience. But then Lukoil, as you know, was a Russian entity, and due to the war, we all had to leave Lukoil. And so now we formed something called Lenol, uh, uh, which is also quite developed quite well. We have about 400 customers already, and good growth for the last 2 3 years, I would say. So that is where we are in terms of the business part of it. But in technology part of it, during COVID, uh, I used to travel a lot for Lukoil for technical these things too. So all the way actually in the initial part of Lukoil's journey, there were not too many technical people east of Suez. So I was basically the only guy. So looking after it from the Egypt to Japan basically was my territory. But later on, we did get people everywhere. So, and then during COVID, the travel had stopped. So I started writing. So I ended up writing about 30 articles during that period from July 21 to December 2023 in the Institute of Marine Engineers magazine, MER. One of the one of the factors to put me into that was because this topic is a pretty big one, and if you want to cover everything for all the way up to usual analysis, the time that I used to have in the regular lectures was not enough actually, the 3 hours. And so I started writing initially on usual analysis aspects of it, and then moved on to the regular tribology and marine lubrication. So there are about 30 articles of mine in the Institute of Marine Engineers magazines, in the MER magazine uh, over that period. And so that brings me to today. So I'm giving lectures now on piloting. In fact, I didn't know that Zoom had changed. So when I started, I was apparently on a very old edition of Zoom and I had to upload it. So I thought I might miss starting this time, but it got uploaded and installed quickly. So we can now start, I guess, unless there are some questions. So I think I'll start. We have about 14 participants now, and more can join anytime, of course. So today, so as I said, it's a pretty vast topic. So I spoke with Pratik, and I felt that if we could split it into several sessions, it might be better to be able to cover everything. So today we'll be talking only about sort of introducing tribology and the main aspects of tribology, like friction, wear, viscosity, and lubrication regime. And then in the succeeding sessions, we will do base oils, additives, cylinder oils, etc., and then move on towards hydraulic oils and so on and so forth. So today's session we can start now. So what is tribology? It's basically the study of friction, wear, and lubrication of interacting surface in relative motion. Characteristics of films of intervening materials between the two surfaces and the consequences of either film failure or the absence of film. The word itself came from a Greek derivative from a Greek word tribos, which means to rub. And it was a very recent invention. 1960s, this started being used as a word to describe what is tribology. And often tribologists like to claim that it's one of the most important subjects that no one has ever heard of. It's not a very familiar term, I would say, in our engineering. Like when I was doing engineering, maybe we covered like 1 3-hour lecture on lubrication. That's it. We, of course, say that lubrication is the lifeblood of our machinery and all that, but we don't talk or learn much about it. But it's a very ancient art. I mean, from a multidisciplinary science, say in the 1960s, but actually the ideas of tribology have been around for a very long time. Humans have been using friction to light fire and so on, and this was probably one of great inventions of humanity. Could give us light, could give us safety, could we got introduced to cooked food, and could be used to drive away predators, and they maybe used to light a fire outside their cave in which they were staying or whatever. And then that was a huge step up for human this thing, learning from say fires being lit up on trees, etc., lightning and all that, and then realizing that you could actually also control it. So it was a huge and then that was a use of friction. Where also has been around as humanity moved towards becoming hunter gatherers, so they needed to improve their tools, etc. So they started learning about filing down and sharpening and so on and so forth. So where was also in use. Similarly, lubrication itself has been in use for a very long time. There are Egyptian hieroglyphics which seem to be showing some fluid being poured in front of rocks that were being dragged for the pyramids and so on and so forth. So there are signs of that from ancient Egypt. There are also Roman relics of Roman chariots, etc., where some fats and oils of animal origin have been found, which were being used for lubrication. So even lubrication has been around for a very long time. And also, of course, this movement from sliding to rolling has been a huge achievement from humanity, from a humanity civilization point of view, because from a very high friction kind of a movement, we managed to come down to very low levels of friction in our movement and so on. And so moving from sliding to rolling itself was also another big and huge achievement for humanity. And as various civilizations interacted with each other, these ideas also spread around the world. Maybe they were invented in 1 or 2 places and then spread all over. It so happens that this movement to rolling was invented in the Eastern Hemisphere and also in the Western Hemisphere. Apparently, this rolling was also invented in the Andes, but for some reason there it did not progress beyond making toys. Whereas in our part of the world, Europe and Eurasia, etc., it slowly evolved into something which we see every day on our roads. uh, since the Middle Ages, it has also been studied. Tribological issues have been studied, and Leonardo da Vinci was one of the first ones to realize that friction and roughness, surface roughness, plays a huge role in the efficiency of the. He was also an inventor or designer of many machines, so he realized that it was also a sort of a limitation factor in the efficiency of the machines that he was trying to make and so on. Also realize the difference between rolling and sliding friction, and some of these his drawings, etc., still exist, which show that he was thinking about these things. Going on to where do we encounter tribology? As you would guess from the background we just described, it's everywhere. For example, you have where taking place in nature. You have everywhere For example, the gecko's feet. In fact, if you have time, you should study this. The gecko, the animal gecko, lizard type of animal, how it sticks to surfaces in such a way that it can even walk across the ceiling, without any issues. Also, so from that level, friction also goes to nowadays. Earthquakes are being studied as a tribological phenomenon, in the sense that earthquakes normally take place when tectonic plates are stuck and then they are released, and energy developed behind in one of the plates is so high that it breaks the friction between the two surfaces and then slide, and then that causes earthquakes. So if you could kind of have seismographic equipments which could measure the kind of tension which is being developed in one of the plates versus the other plates, then you might be able, and also understand the uh, coefficient of friction between these two surfaces, then you could probably predict friction coefficient taking place. So even that kind of thing is being studied. It's of course, as I said, in nature. So as you would understand, all varieties of machinery, we have tribological issues coming up. Similarly, tribology plays a huge role in our life. Probably don't pay enough attention to something being a tribological issue. For example, we wouldn't be able to move without proper lubrication of our joints. There is a fluid called fluid which is captured in a synovial capsule, which helps the movement of our joints. And when there is something going wrong, either fluid production is not enough, the surface is deteriorated, then we have a lot of problems. For we have, say, arthritis, rheumatoid arthritis, etc. So then that becomes a huge. Uh, about more than 1 million knee replacements and hip replacements are taking place around the world per year. Even this replacements are resulting in metal on metal moving inside our body, metal on ceramic moving inside our body, metal on plastic moving inside our body. How the wear particles generated would be removed from the body. How long is this replacement going to last? How the wear rate will be? What will the wear rate and how long will it? These are current topics in biotribology. So tribology has now progress further into having sub subjects, like you have nanotribology, you have biotribology, and so on, geotribology. So biotribology currently has this as a major issue. For example, our lifetimes have increased. So would it be good to change, have a knee replacement at the age of 50? If the wear rate is too much, then you might want have to have one at the age of 70, 75 or something like that. So when does the appropriate time for which kind of a knee replacement to be done so that it will last for the life of that person or something like that. So those are things being studied currently. We wouldn't be able to blink without proper lubrication of our eyelids. And just by the way, we have not yet been able to develop a synthetic synovial fluid. So that it's such a complex kind of a molecule or fluid which has been evolved in our body that we have not been able to replicate. Same goes for tears. We have not yet been able to develop a synthetic proper tear film, because it's a very sophisticated thing. There is a oily kind of a fatty layer which helps the film to stick to the eye surface. Then there's an aqueous layer which allows the movement of the surface, the film of the film surface to move around. And then there is again a lipid layer which prevents evaporation of that fluid. So it's such a sophisticated film that we've not yet been able to replicate. And it's so thin that even a tiny speck of dirt gets into our eyes, we are in trouble, we are in pain. So that thin film we have not been able to replicate, and there are various glands which actually this film, and then that comes together as our tear. In a more sort of less technical, you could say, way, people use shampoos which promise smooth, silky hair. Again, there are some particles in the shampoo which coat the hair follicles, and the hair follicles can slip past each other easily. So you have smooth, silky hair. There are some shampoos which promise volume. There are again starch and protein particles in the shampoo which stick to the hair follicles, and the hair follicles cannot slip past each other easily. So you have the hair appears to have more volume. So you could have this thing. So what I'm trying to drive at is tribology plays a very very important role in our lives. We are not paying it. We wouldn't be able to walk across a surface without the right friction, or we wouldn't be able to grip something without the right friction. And our cricketers, in some cases, they will apply saliva and all that. In some cases, they will rub against the surface. They are changing the frictional properties of that ball. So it's there everywhere. We are not just paying attention that this is tribology in action in our lives. So moving on to the main aspects of tribology, the main components of tribology, one is of course friction. And we know that when we want something to move, we need to apply some force to overcome that friction, which is preventing it from moving, right? And there are some kind of, within inverted commas, laws of friction going on from the times of Leonardo da Vinci, actually, quite well established, which work in general conditions, but not in extreme conditions. For example, at nano levels, they might not work. In vacuum conditions, they might not work as well. But in general, they work well. So one is that friction is proportional to the normal load. What does that mean? Say this was a block that we wanted to push or pull or whatever it is. So then we are to certain friction is preventing that movement, right? Or it is happening while it's moving. We are applying force to overcome that friction. But if there were two blocks, then the force would increase. So friction seems to be proportional to the normal load. That's what that law kind of tells us. Friction also seems to be independent of the apparent area of contact. Had that block been on this surface, whether it had been on this surface or on that third surface, this surface, roughly the force of friction remains the same. What really matters is so this is you could say the apparent area of contact. What that means is that when we look at the surfaces at a very microscopic level, this might even be a glass surface, whereas this might be a block of wood or a block of iron or something like that. So when you look at this surface, of course, that the surface looks consists of asperities and valleys as a rough surface. But even glass at that microscopic level has asperities and valleys to some extent. So real contact takes place between the asperities on this surface and the asperities on this surface. So the entire area is actually not involved in that contact. So only the asperity contact is what matters. And so going back to this, so with one brick, maybe some number of asperities were in contact. So the friction force was X. But now if you have doubled the force, then the friction force is likely to increase because more number of asperities are going to be coming into contact. So that is how that works, right? And also, we know that once bodies begin to move, the coefficient of sliding friction is usually less than the coefficient of static friction, right? And how that is explained is something like this, that under static conditions, many of the deeper as well as the shallow asperities are making contact, so large number of contacting points. But once motion begins, there is a certain lift off taking place. And so fewer contacting points. Some of the deeper asperities still make contact, but some of the shallower asperities might be losing contact. So it is easier for the body to move along. And so usually you have static friction being less than sliding friction. And of course, the other major aspect on the coefficient of friction is the kind of surfaces. So steel on steels, aluminum on steel, ice on ice, Teflon on steel, Teflon, all would have different coefficient of friction because of nature of the contact making and how the surfaces interact with each other and so on and so forth. So those are the three important things which have an impact on the coefficient of friction. What causes the friction? Under load, under no load, maybe the asperities are just barely making contact and there's not much much interaction taking place. But as the load increases, the load starts starting to deform the asperities. Sometimes the asperities are deformed to a level where they start even welding together. At the tips of the asperities, they start forming micro welds. And so that force now required to move it keeps on increasing, right? Similarly, some asperities might get interlocked and then prevent movement, and then you need to apply a force to form grooves in these materials so that they would move, and so then again asperity contact causes friction. There is also, of course, rolling friction, which is much less than sliding friction, but also it has to be, it is there when a body is rolling, eventually it will come to a stop because there is rolling friction, right? Some types of friction that one hears about, one is of course dry friction. In that photo, in our diagram where body was resting on a surface. If there was no film of lubricant separating them, then it could have been dry friction. Right? But if there had been some film separating those two surfaces, then it would have been called lubricated friction. There is also, of course, skin friction. For example, on board ships, we are aware of barnacles, etc., coating the ship surfaces and then slowing down the vessel, or you needing more energy to drive the vessel at the same speed, etc., etc. There is, of course, rolling friction, which we just spoke about, and there is static friction. Like for static, for example, in this place, if this guy loses normal load for a very millisecond also, he's going to slip down because the coefficient of static friction is much more than the dynamic friction. So he's going to slip down all the way. If all that friction is allowed to go unchecked, we would end up with some kind of wear, possibly, right? And in literature, you hear about many types of wear. For example, adhesive wear, abrasive wear, corrosive wear, which are the main components of wear in our combustion spaces. Then there is cavitation, erosion, fatigue, fretting, brinelling, etc., which are other forms of wear which we normally would encounter in our marine kind of a environment. So just quickly go through marine in the marine field. That could lead to addition, like as we said, sometimes they might form welds together, and when we keep applying a force, we build those, and we call that as adhesive wear has taken place. So resulting in the transfer of one material to the other material, to the other surface, etc. Where debris formed typically would take place in areas which are not sufficiently lubricated. So one of the aims of most lubrication systems is to form a thick film. We call it thick film lubrication. And the aim of that thick film lubrication is that it should be so thick that the thickness of the oil film is greater than the sum of these asperity heights. That is the thickness that normally one would aim for good thick film lubrication. And where we lose that, then this asperity contact is possible, and then we have wear coming in as a possibility. Some examples of adhesive wear typically taking place in areas where the film is lost, right? And for example, valve stem is a difficult place to duplicate, and it is commonly known to have adhesive wear taking place on the valve stem, etc. The normal running in that we have in the initial stages of our machinery, that is also a kind of adhesive wear only, but it is actually a useful form of wear in the sense that in that period, actually the surface roughnesses, excess surface roughnesses left behind by the machining process is being polished off, so that you end up with a surface which will last for the rest of the life of that machinery. But sometimes you reach a level of roughness, the oil film is lost, or enough, or the surface roughness is so high that contact does take place. And when that excessive kind of contact takes place, that we know by a term called scuffing, that is a very extreme form of adhesive wear taking place, right? So as I said, good thick film, thick oil film is the mechanism that we normally use to prevent adhesive wear from taking. Abrasive wear is another form of wear, and in fact, it is the most common cause of loss of component life. What condition? When a hard moves material or plows material from a softer surface, you could say that this is abrading the other surface. So, for example, filing a piece of wood, the hard surface is removing particles from that soft surface, and that is causing abrasion of that surface. Abrasion typically involves, the mechanism could involve cutting, fracture of the materials, displacement of the material. For example, if a dirty oil passing through a bearing surface, maybe the bearing surfaces might not be worn off, but it might be forming grooves in that. So repeatedly grooves are being formed and so on. Or sometimes whole grains being pulled out. Most of the metals we are dealing with are crystalline metals. So groups of crystals might be dragged out. So that would also cause excessive wear, right? So abrasive wear is for something called two-body wear and three-body wear. Two-body wear is the hard surface is directly acting against the soft surface. So again, removing material or making grooves in the softer material, that would be two-body, direct contact between. Excuse me. Three-body is where the hard material is actually trapped between the two surfaces. For example, lapping, for example, would be an example of three-body. The hard material is trapped between the two surfaces that we are lapping. So then in the third three-body wear, one more important parameter which plays a role is the thickness of the oil film versus the thickness of the dirt, the grit or the hard material, right? So for example, the oil film was 50 micron here, and the dirt was this 2 micron, 5 micron. That piece of dirt is likely to pass through without causing wear. So we are not really worried about that. What is going to be worrying us is the size of a grit of roughly 40, 50, 60, 70 micron. That would be really dangerous. That would rub against the surface and that would cause wear. And this idea leads us to another this thing. What level of filtration do we need to apply for this oil film? So we are looking at a 50 micron oil film. We might have 30 micron mesh filter or something. But if we are looking at a 10 micron oil film, we might need to have a different kind of an oil requirement, right? So for example, main engine crankcase oil, hydrodynamic lubrication, good thick film lubrication. Typically, main engine crankcase oil filter or auxiliary diesel engine oil filter, main filter would be around 30 micron, 40 micron, 50 micron, that level, right? But for hydraulic oil film is going to be very, very thin. We're going to come to that a bit later, but let's talk about it right now. So oil film for that would be much less. So the filter for that would be also much more, the mesh size would be much less. So typically abrasive wear takes place in most equipment, but specifically in our combustion space, we are always worried about cat fines. Cat fines are these hard particles. You are all aware of cat fines. Aluminum, silica, from the cracking process in the refinery. Sometimes some of it gets carried over into a residual fuels, and then that could cause wear. It can cause two-body wear, for example, or even three-body wear. So if the cat fine particles are trapped between the piston ring and the liner, you could have three-body wear. But sometimes the cat fines get embedded either in the ring or in the liner, and then that could cause two-body wear, right? Similarly, for example, nowadays you have very low sulfur, but sometimes high BN products being used, or so some of the alkalinity accumulate there, limestone kind of a deposit, and then that could cause two-body wear of the liner, for example. This was that case I mentioned earlier. Dirty oil rubbing through the piston, through the journal bearing, and then causing grooves in the bearing. So adhesive wear and abrasive wear, you could see more mechanical kind of wears. Corrosive wear is those wears combined with the environment causing corrosion. Many environments might have chemical reactions taking place on the surface. Could be acidic, could be moisture, could be various other components which could be degrading the surfaces. Usually when these reactions take place, soft films are formed on the surfaces, softer than the base metal. So soft films are being formed because of the environment in which this is happening. And then rolling, rubbing, etc., that film is easily removed. And if the environment continues to be reactive, again it is formed and again it is removed, and that's how it proceeds, right? And so the wear, mechanical wear by itself might have been, the rate of wear might have been this. Corrosion by itself, left undisturbed, maybe the rate of wear would have been this. But when it comes together, that rate of wear dramatically shoots up. One of the areas which was more prone, it's slowly going back into the background because sulfur content of our fuels is less. But all along in our until about 2020, of course, we were always running few engines with stoichiometrically excess oxygen conditions. So all the sulfur in the fuel would get oxidized. And these reaction rates are different for different temperatures and pressures. So about 15 to 20% of the sulfur would eventually end up forming sulfur trioxide. And water is also, of course, a component of the combustion of the hydrocarbon fuel. H finally forms water. So water is around, acid gas is around. So long as it remained gases and left with the exhaust, we wouldn't really bother. But once water is formed and this is formed, and then the temperatures of the surface are suitable enough for this now as liquid acid to start depositing on the liners, then we used to have this problem of cold corrosion. And that's why all our cylinder oils used to be so alkaline. Currently, alkalinity of cylinder oils is in this range, 15 to 140 BN. So depending on the nature of the wear, nature of the machinery, nature of the sulfur content, the BN of the content we used to wear. So you're familiar with this cold corrosion that had become very common in the earlier era before VLSO. Moisture causing hot corrosion is another issue. Sodium and vanadium deposits, eutectic forming eutectic alloys, which are high, very low temperature liquid, very hot corrosive liquid, and then that starts cutting through the valves, etc. Fatigue is another major form of air. Fatigue, we use this term in everyday life also. Like we exert too much, we say fatigue. When materials were exerted too much can fail due to fatigue. Not necessarily they are stressed to the limits of their elastic strength. Even within the limits, if they're stressed too often, then you could have fatigue propagated cracks forming. Cracks could start on the surface or subsurface. So both mechanisms are there, and fatigue could eventually cause a lot of damage. Rolling and bearings are particularly prone to fatigue. Rolling and bearings like ball bearings, etc. In a journal bearing, one does not necessarily expect fatigue because the nature of the surface is a sliding contact. But in a rolling element machinery, this say this ball is rolling on this surface. So at that point of contact, there has to be some friction. It's called traction. So when this is applied hundreds of thousands of cycles, eventually traction force might cause a crack to be initiated. As the crack as the ball rotates further, the traction force may be trying to close down that crack. And in the very initial stages, it might even weld back together. But had we been using lubricants to prevent this from happening in the first place, or to extend the time before which it happening, then this surfaces now are wetted surfaces, and if sufficient lubricant has got entrapped inside and we are trying to close down that crack might, the lubricant inside, trapped lubricant inside might create a kind of a hydraulic jack effect inside that crack. The crack might actually propagate faster than had it been dry in the first place. So we need the lubricant to prevent this from happening or to extend the time before which happens, but eventually it does result in reducing the life of that equipment. Fretting is another common mechanism, reciprocating motion in a very limited surface, very hundreds of thousands of cycles. Eventually, adhesive wear causes for particles to be formed, and then particles get work hardened, and eventually abrasive wear starts in, and then so the wear rate starts. Maybe the wear rate might start like this, but then it goes like that. You're familiar with the examples of fretting. This used to be quite a frequent. Any nut bolted joint, any riveted joint not properly pre-stressed, you could have fretting coming into play, right? Brinelling is another wear mechanism in which, if you remember from college or while studies, Rockwell Brinell hardness used to be tests in which a wedge-shaped device was dropped onto a test piece, and you measured the depth of the wedge and looked at a chart and said this is a Brinell hardness. So Brinelling implies actually displacement of material, not loss of material. False Brinelling ends up looking like that, but is actually loss of material. False Brinelling typically takes place in equipment which is not in use. But that equipment is subject to some minor vibration, light vibration from other equipment around. So in that light vibration, say there was some ball bearing is separating the shaft in that equipment. So gradually the bearing is sort of vibrating and removing the oil film which is separating it from the shaft. Eventually metal to metal contact is taking place, and that metal to metal contact eventually results in a dent, a kind of a pit forming in that. But the pit looks very much like a dented pit. So that name has stuck to it, like false brinelling has taken place. Cavitation is another important mechanism. You're aware of cavitation. Basically, fluid passing through a where vapors of the fluid itself form bubbles in the body of the fluid. Air is not necessarily required, but air being there makes it worse. But bubbles of the fluid are formed, and then if the same fluid passes through a high pressure zone where the pressure is so high that the bubbles, the vapor in the bubble starts coalescing back into the liquid, so the bubble starts collapsing, and then you have implosion taking place. And if that liquid jet forms near a surface and hits the surface, then you could have cavitation pitting coming in. So some examples of initial early ME engine exhaust valve operating device had cavitation issues, and they changed the design. Hydraulic components, for example, in a spool valve, the spacing is so tight that very likely, high likelihood of this cavitation impact taking place on the surfaces and so on, and causing cavitation. Current discharge is another mechanism whereby many rotating equipments have a tendency for charge to accumulate on the shaft, and that charge looks for a place to discharge from. And one of the nice easy places to discharge from is through the oil film between the bearings. And when current is being discharged, of course, spark erosion is taking place basically, and can be damaged quite rapidly. So to prevent all this from happening, we bring in some form of lubricant to prevent friction, prevent wear, extend the life of components, and so on and so forth. Excuse me. And one of the main key aspects, key requirements for lubrication is the right viscosity. So viscosity is the most critical property of a lubricant because it has impact on so many properties of a lubricant. Of the oil film, thickness, strength, wear rate, etc. Everything seems to be coming back to getting the right viscosity. And viscosity is a physical property. It's a natural property. It is basically uh, the intramolecular attraction between the stuff which makes up that fluid. If it is high, then the viscosity is high. If it is low, then the viscosity is low. And so, for example, water has a low viscosity, forms droplets quickly, whereas chocolate slip relatively has a very high viscosity, so it forms a very long tail, etc. But of course, being a physical property, physical conditions changing, viscosity changes. So if you were to heat this up, then of course its viscosity would drop nearly to that of water, right? Coming to engine viscosities, there are two varieties of viscosity ranges that we use. Engine oils go by something called the SAE viscosity. The main engine crankers are SAE 30, and the auxiliary engine is SAE 40 mainly, and cylinder oils are SAE 50. Basically, what those viscosity imply is this. SAE 30 is an oil whose viscosity is between 9.3 CST and 12.5 CST at 100 degrees centigrade. 40 is between 12.5 and 50 is between 16.3 and 21.8. So these are the different viscosity ranges that typically we encounter in our marine field. Okay. Secondary grades, the ancillary grades go by something called the ISO viscosity grade. ISO viscosity grades go from 2 to 150. And the nice thing about the ISO viscosity grade is actually the viscosity actually tells us the viscosity at 40 degrees. So the ISO viscosities are measured at 40 degrees centigrade, and like 100 viscosity is actually 100 viscosity is the midpoint of that range. Of course, there is a 10% tolerance band, just like there was a tolerance band in this. There's a 10 kind of a tolerance band so that for manufacturing. So if you were to call an oil 100, it could have a viscosity between 90 and 110 and still be known as a ISO VG 100. So viscosity, there are a couple of terms that we are familiar, or one of the terms we are familiar with is viscosity index, which gives us an indication of how fast or slowly viscosity changes with temperature. High viscosity index implies slow change in viscosity with temperature. Low viscosity index implies very fast change in viscosity. And there is something called pressure viscosity coefficient. Viscosity also happens to go up with pressure. Higher the pressure, viscosity tends to go up. For most lubricants, and it can be quite dramatic. Like pressure doesn't increase by twice or thrice or 10 times. It can go up by 2,000 times, 3,000 times, 5,000 times. So basically the oil, instead of behaving like a liquid, starts behaving more like a semi-solid. It's that kind of dramatic change taking place during the time when this pressure is being applied. Lubrication regimes, we have about 10-15 minutes, right? Yeah. So everybody familiar with hydrodynamic lubrication, the body of the machine, the movement of the machine itself causes the film to develop. For example, in a journal bearing, as the journal starts to rotate, oil film gets trapped into a narrower and narrower wedge where that pressure rise takes place, and that keeps the journal afloat in the bearing, right? So that is rotary hydrodynamic lubrication. In a piston ring in the liner, as it moves towards CDC or towards BDC, a wedge effect is formed between the piston ring and the liner, and that provides a hydrodynamic lubrication. Of course, we use hydrodynamic at And there we are relying on other properties of the oil like boundary lubrication or anti-wear properties, etc., to prevent wear in those areas. But throughout its motion, ideally, we would like to have good hydrodynamic film to minimize friction, minimize wear in a piston alignment. Thrust bearings also basically, again, this is sliding hydrodynamic load rotations, hydrodynamic lubrication. Thrust bearings are also sliding hydrodynamic lubrication. This is rotary hydrodynamic. And oil film thicknesses can range between 20 and 60. Actually, in literature, normally in normal machines, you look at it from a 20 to 25 micron point of view. But in our industry, as the bearings became larger and larger, you could go up to 60 to even 100 microns as being the oil film thickness in the largest size bearings in our industry. Also, yeah, but in terms of sliding hydrodynamic, the film thickness rarely exceeds 10 micron. Thrust bearings are considered to be one of the most successful forms of hydrodynamic lubrication because earlier idea was, thrust is like this, so the bearing surface should be like this, right? But that wasn't working until this idea of having a tilt in the pad so that oil film would enter and form. That became so tilted pad bearing probably one of the most success. In fact, I would say thrust bearings we are barely looking at. They're doing, I mean, that's the thing which is moving our vessels, but we are barely looking at them because they're doing such a great job. Hydrostatic is a kind of a subset of hydrodynamic lubrication in which we won't wait for the machinery to develop that oil film. We'll supply the oil at a high pressure and then that will keep the general afloat or the machinery going, right? Sorry. Elastohydrodynamic is a different form of lubrication. Sorry, I did not mention this here. No, I did not mention it yet. Okay. So there are basically two types of contacts. One is a conformal contact where the two surfaces are conforming with each other. The radius of curvature of this surface and the radius of curvature of this surface is almost same. So in a journal bearing, that's a conformal contact. But in a ball bearing, the radius of curvature of the ball and the radius of curvature of the rollers are the raceways are very different. So that is a non-conformal contact. The surface is not conforming. And that usually ends up point of line and rolling action. Here we are looking at sliding contacts. Here normally we are looking at rolling contacts. So under those conditions, here we can understand that the oil film was quite widespread, the contact was quite widespread. So the unit load at any one point was relatively small. But how does that work here when the unit load can be immense here at a very small point or a line or something like that? How does that survive? And that is basically explained on this basis that under those conditions, there is no material which will not deform. Some deformation will take place. And if that deformation results in some kind of a pocket in which oil gets trapped, and then that entire load is passing through that small pocket, load is very high, pressure increases, and then that pressure viscosity coefficient comes in, and that oil starts behaving more like a semi-solid. For that point at that time, then this whole thing is happening somewhere else. But at that point, at that time, that oil is behaving more like a semi-solid, which prevents this metal-to-metal contact taking place, and our body-to-body contact provides lubrication at that point in time. So that is elasto-hydrodynamic lubrication. Of course, it can't be very thick because the oil will spill out if it was too big, and that pressure rise would not take place. So usually it can be as low as 1 micron, but max goes to 10, 12 micron or something like that. That will be the area. So where is it useful? Virtually in all rolling contacts. In a ball bearing, for example, we don't want the ball to slide on the surface. It will get damaged in no time. We want the ball to roll so that this kind of mechanism is actually developed, Similarly, spur gear, for example. Towards the extremities of the spur gear, you have sliding contact taking place, so hydrodynamic lubrication. But in that area of maximum load transfer, around that pitch circle, there that contact is more of a rolling nature. There again, you have elasto-hydrodynamic lubrication. Squeeze film is a form of lubrication where, as bodies come closer to each other relatively rapidly, because of the oil viscosity, the entire oil film will not get squeezed out immediately. Some of the oil will get trapped within these two surfaces, right? And for that few milliseconds, completely squeezed out, that also provides a sort of a film which is separating the two surfaces from each other. So these are really, really thick, thin forms of lubrication. We talk about, 1 micron, 2 micron, 5 micron kind of a thing. So just to sort of, contrast with what we normally, because we call this thick lubrication, but hair thickness, human hair thickness is 70 microns. So when you talk about 5 micron and 10 micron forms, it's not really very thick. But so maybe in tribology, we should sort of inverted commas thick film lubrication, you could say, because there is another function which we are now coming to, which is thin film lubrication. That is where we are not able to form all forms of lubrication. Then we are squeezed down to a place where asperity contact is likely to take place. But we would still like to prevent friction and wear from taking place. So there we have films which stick to the surface. Anti-wear properties, anti-boundary lubrication, extreme wear properties, etc., which will form static films. All along we were looking at dynamic films forming. Now we want static films which will stay there even when this contact takes place. There is a film which is separating the two surfaces. So that is where some compounds stick due to physi-adsorption on the surfaces, and some form a chemical attraction, and then that sticks, that forms a film, and then that provides protection against wear under those kinds of conditions. EP is another extreme kind of anti-wear property where the reaction is quite strong, very highly, the strength of that film is pretty high. And then that provides that film protection under extreme. So actually we call it EP, but actually that extreme pressure at the asperities results in high temperature. So actually the high temperature which sets off this reaction of the EP film on the surface. Then we come to solid lubricants. Everybody is aware of molybdenum disulfide, moly coat using that consists of grease, which is one of the additives in that is a solid lubricant. This is the moly structure. This is the graphite. Graphite was the original famous solid lubricant. Basic idea is the same. The shear strength between the laminar layers is very weak. Easily breakable bonds in the laminar between the surfaces. So, but in under different kinds of forces, it might last longer, but under shear, it breaks off very easily, and that provides the lubrication at that point in time in this. So, moly, for example, say this is a body which is rolling on this surface. So we have moly coat in the place. So as the body is rolling and the grease is doing the job of lubrication, the solid lubricants are actually getting entrapped between the asperities here and on the asperities on the counter surface, gradually developing solid films on the surfaces. And then when the load reaches a level where cannot be supported, there is contact. Now you have solid films contacting each other. And then same kind of in EP, solid films which are formed, here solid surfaces which are formed which shear easily and then provides lubrication at that point in time. So that brings me to the end of today's this. Any questions? Would be
Session,
glad
like
to.
everyone was very, very engrossed in the session. And I would open the stage to everyone if they have any question they want to ask. Sir, and this is a multi-part series, so we'll be having one more session next month. So if anyone has any question, they are like free to ask.
Yeah, good afternoon. This is Pankaj here. Yeah. Thank you, sir, for the nice presentation. Actually, I joined a bit late because I'm in Africa time zone, so I just able to join. So it was informative, sir. I need some of your advice because I'm a technical superintendent. So I have a case. One of my friends shared some photo. I don't know. Coincidentally, he shared this morning only. So he was looking for some advice with respect to the stern tube bearing. Stern tube bearing. So I will share some photos, sir. Because the stern tube bearing, the top shell is having some like uh, groups because of some, I think some foreign particle came inside the bearing and the shaft and make some scoring marks. And bottom shell is okay. So I will share those photos. I need your advice that, like, because they need to use that, they are in the dry dock, so they need to use that bearing for the time being because it will take time to fabricate and all. So how to make the like those groups a bit smooth and to get a hydrodynamic effect maybe stern tube is not having a purely hydrodynamic because of its speed of rotation is not so high. But I just need your advice on that matter, sir. Like how to like shape out these grooves, and I will share the photos.
Do you have the oil test report also? Visual analysis report?
Yeah, I will check. I will check with him. I will check with him. Maybe because now in dry dock they already removed the this oil and they discarded it. So I will check on that.
Okay. Because something has caused those grooves. So that oil test report might give a hint as to what was causing it. Because the same thing should not cause it again in the future also, you know.
Yeah,
So
correct. Preventive
better
measure.
is
Yes,
to
sir.
know what is causing it. Is the surface of the shaft is very smooth and all? Has that been checked?
Yeah, I will send you the photos, sir.
Maybe you
Are
could
you
maybe you could send it on my email and then we could chat on that separately. Want to
okay?
do that?
Okay, okay.
Yes, sir, I will
Yeah.
connect you with Pankaj, sir, for that. And anyone has any question, so that or we can wrap the session.
Hi, good afternoon, sir.
Yeah.
Fateh this side.
Hi,
Hi, sir. How are you, sir, today? All doing good?
I'm fine. So
Sir,
just to inform everybody else, just 1 second, just to inform everybody else, Fatbir to connected me to your group actually to Pratik and asked me to do this session actually. Yeah, go ahead, Pratik.
yes, sir. Thank you, sir. Sir, actually, no, I wanted to have some discussion on this bearing lubrication. That one important thing you took out in your session regarding this, especially this motor bearings. Motor bearings lubrication. Usually now what we have a tendency like we measure the vibration, there is no noise coming, and all these things we check, and suddenly we feel that no need to overhaul the motor, or no need to change the motor bearings. One is this thing, and second thing is that how often we need to lubricate the bearings. That is, and so often sometimes we see that we feel that yesterday the motor was running fine, everything was okay, there was no noise, no vibration, and suddenly what happens the next day, because of the motor bearing failure, this motor burns out because the stator and rotor, they both touch each other. So what thing you will advise in this?
Grease lubricated or oil lubricated?
Grease lubricated.
Okay. So grease lubrication. Actually, we're going to be talking about grease lubrication probably in the next
Okay.
session.
Okay.
But like sealed bearings.
Any kind of bearings, like open bearings. So usually we do lubrication for the open bearings only. Sealed bearings, we don't do the lubrication.
Okay. So when you do the lubrication, what comes out from the drain plug? When you open the drain plug, what is coming out?
No, this is just a general question I'm just asking, not about a particular problem I have faced. General means what should be the tendency of us for lubrication the bearings? What should be the interval?
One is of course, yeah. So the greasing intervals and all that you're taking care of.
Yeah. Yes.
Okay. Greasing intervals you're taking care of. How much quantity, like how do you lubricate with what kind of a grease?
Yeah. Because many times we feel that like now people they just lubricate any now and then, like after once a week, or sometimes once in 15 days, and then they end up in over lubrication also.
Right.
So
that's what I wanted to drive at. More bearings fail from over lubrication than under lubrication.
Okay.
Because for some, if you have opened a seal bearing, there is barely a film of grease inside. But for some reason in our industry, when we get a grease gun in our hand and we see that zerk of a grease, this thing, somehow we feel that the grease has to come from every nook and cranny and then we'll be satisfied. But actually more bearings fail from over greasing. So that is one of the key issues over there. Secondly, the spacing between the greasing, because obviously the engine manufacturer and the grease manufacturer, the bearing manufacturer have designed this and used this for a much longer than what onboard. So they have determined certain periods and the kind of environment in which the bearing is working, and what kind of bearing lubrication and what kind of a bearing re-lubrication schedule that should be followed and so on. So if you are basically following all that, there should not be that many issues. So exactly. So if you are using the right lubricant, right grease, and re-greasing around the right intervals, and preventing the environment from having an impact, water getting in or dirt getting in and so on, then more or less you should be okay following the lifetimes of the bearings. But what you are saying is actually interesting, because vibration should be catching it earlier, actually. I mean, or of course, thermal imaging. Thermal imaging and vibration should be catching it. I mean, normally that is the rate at which, like, because oil testing is not a continuous process. So usually usual analysis comes towards the end of, finding out what is going wrong or something like that. But so vibration starts off much earlier, and temperature rise also starts off much earlier. So thermal imaging or vibration should be catching this quite early. I don't know why it's not, unless it's not being done properly or something.
Yeah,
Even if you're So anyway, we'll be talking about grease a bit in probably the next session. That there are many interesting things about grease that sometimes we kind of overlook. So we'll talk about it at that point in time.
Sir, can I share one point on this? Myself,
Yes,
Khemchand Khatri. Sir, Fatehbir sir has raised this, since he has raised this point. So what I have come across is most of the time this failure is happening due to the wrong practice, because most of the time it is not being checked by or inspected by the senior chief engineer or the second engineer. We just instruct the trainee ETO or the ATO who goes there. He's just opening the inserting point or the inlet point. They are not removing the outlet port so that the new grease can come out. And what happens over the time, what happens, though they are using that pneumatic greasing pump or all, the grease gets accumulated into that. So what I have found, like even I have said with very senior chief engineers from our institute, and they have told me that this is the thing we have to take care. And the most of the time, if you see in the manual, they are done on the basis of running hours, or either we can go on a 3 monthly basis. We can chalk out that which motors to be done in 3 months and which motors to be done in 6 months. But the main thing was the wrong practice.
Very true. And that's why first thing I asked Fadbir was what is coming out of that relief plug, because that gives you an idea of what was happening inside. If nothing is coming out, that means the grease has dried up. If water or something else is coming up, there is some contamination inside. So many things are learned from what is coming out, actually. Actually greasing is somehow, there are a couple of things. In fact, now that you have brought up that, I didn't want to say that we are not doing it right, but 2-3 things we don't do right. One is greasing. Of course, we delegate it down too far down the line to somebody who might not be aware of how critical that action is. And secondly is usual analysis. Usual analysis, somehow we feel it is, very tertiary to what our purpose, I mean, this thing. But getting the right sample is the key to usual analysis. Otherwise, that entire exercise is a waste of time. So you're collecting it. If it's not representative of the what you want to test, then it is a useless sample. And you often get wrong information, take the wrong action based on a sample which is not correct. So that is another thing that senior engineers on board should be actually, educating these guys whom we are delegating to do all this. Very, very, very important.
Sir, I have one doubt, sir, myself. Sir, just since we have raised this bearing lubrication part, Like we are supposed to do this lubrication by the pneumatic gun uh, while running of the motor or when it is in standstill condition. Like I have doubt in this.
If possible in standstill, but as you are pumping it in, you should rotate the shaft.
Okay, so thank you.
That would be the ideal condition. And then watch for what is coming out.
Okay, so thank you.
Yeah, sir. Just to add on our previous discussion regarding that practices part, I would like to add on one point here because it's a new update. Now we have ongoing this SIRE 2.0 in the tanker industry. They are doing it SIRE 2.0, and parallel is in like later they implement in dry ships also with that right ship inspections and all. So in this SIRE 2.0, what they have introduced is like a human element, the process control, and the mesh and the hardware. Three things they have introduced. For example, if there is a defect found by an inspector, let us say some motor is damaged because of the bearing thing. So now he will before in the SIRE inspections he used to write like the motor is damaged, so and so motor. But now it will be a three observation. He has to write first the motor is damaged. Second observation he has to write that whether there is any defect which has been raised by the vessel, and what was the follow-up with that incident, like the preventive measures. If you find that process is being done, he will write it was satisfactory. Otherwise, he will write that it was not reported, it was not followed. And the third thing is the second is reporting, and the third is the process. Like what is like being followed to prevent this. So these three things, these two additional things now the IMO has implemented. First, they have implemented this OCIMF by OCIMF. This human factor has come. This is just a new update because SIRE 2.0 has just been implemented for last 3 to 4 months. So now they are catching on this part. They are not only seeing the defects, they are seeing the reporting of the defects and then the process which is associated, why it led to this and how you prevent this. So this part is now being taken care. Now I had inspection 2 days back. So we had a three observation which as per previous inspection there should have been only 3, but now they have given 9 observations because each observation is now turned into a three, and now vessel has to give response why they did not raise the defect, why they did not check it. So this thing is now being implemented and is being like scrutinized by this oil majors and this all business industry. Yeah.
Very, very nice. Very nice. Good to hear. Because I am no longer sailing, so I'm not in touch with all this IR, this thing. So, but now that you have brought it up, maybe I'll read it up also. But because we are talking so much about bearing lubrication, wanted to just highlight that sometimes we don't think through what we are doing on board. For example, same example of your motor, say bearing is, I mean, we opened it for servicing and we find that the bearing is loose, right? So at least during my sailing days, option used to be let us, punch a few marks on the shaft and then the bearing will be tight and then we'll go on. And then we fit and then, but if you see from a heat transfer point of view, what we are doing. So normally the shaft, the bearing, when it is tight on the shaft, when it is running, the bearing is developing heat, right? But that shaft, because it is tight on the shaft, the heat transfer takes place into the shaft, and the shaft of the motor is cooled by a fan, and that keeps the temperature more or less in play, in control. And some of the heat, of course, gets radiated to the body of the cover of the bearing box, and then radiated outside. So you can imagine like some heat transfer into the shaft by some convection taking place, then outside body, the box, air is cooling that, and also so you can imagine this is happening. But now we have punched marks on the shaft and then we have fitted this. The area of contact between the bearing inner race and the shaft is now very, very less compared with the earlier area of contact. So heat transfer now is very much reduced that way. So now it starts getting hotter. All the
Yeah. Thank you, Sanjeev sir, like for awesome session, and thank you everyone for joining in. And thank you for making it very interactive. And we'll hope to see you next month also with throughout the session. And for those of you who could not join live, we will be uploading the recording very soon so that you can watch and revise and learn from the wisdom of Sanjeev sir himself. Thank you, sir. Thank you once again. And
welcome. Thank you. Bye.
Thank you.